So hello everyone. The agenda of today's video is to discuss the AlexNet architecture. So AlexNet is a very popular deep learning architecture that has been around since a long time. In this video, my motive is to discuss the paper, the AlexNet paper, and do some analysis on the architecture and to see how it fares with the architecture that are more popular today, like VGG architecture, ResNet, etc. So as you can see, I have opened the original paper that is authored by Alex Krzyzewski, Elias Huswerker and Jeffrey Hinton. So these are all very popular scientists, and you may have heard of Jeffrey Hinton before. He is also popularly known as the father of modern AI. So let's start. So this model, like ImageNet dataset, I think you have all heard about it. So it is a very popular large database actually. So it's 1.2 million high resolution images, and every year it conducts a contest in which the different scientists from across the world participate and submit their results. So in 2010, in the same contest, this paper AlexNet model got the first prize. So if we see in the abstract, first it writes about the dataset, that is ImageNet, and it says that it contains about 1.2 million high resolution images. That is pretty huge. That's actually huge dataset, and this cannot be trained in our home. It requires high-end servers to get trained, and it has 1000 different classes. So it is a classification problem that they're trying to solve, and it has 1000 different classes. You might be familiar with image dataset, in which we have handwritten datasets ranging from 0 to 9. So we have 10 classes. You have UC for 10. There also we have 10 classes. C for 100, we have 100 classes. Similarly, in ImageNet we have 1000 classes. So this is the AlexNet architecture. They have mentioned the salient features of this architecture, which we are going to deep dive about. Now in this video I am going to analyze the paper and try to figure out what were the main features of this model. In the subsequent video I will try to code it and try to explain each and every line of the code. So this is just introduction. You can read about it, like it describes all the dataset that they have trained. For example, the Caltech dataset, the CIFAR dataset, the MNIST hand recognition task, etc. And they have mentioned how their model fared with against the datasets. Now this is the detailed description of the dataset ImageNet. So ImageNet, the overall ImageNet dataset is 15 million high resolution images, and it belongs to 22,000 categories. So like the ILS, VRC, this is a subset that we have talked about in the starting of the video. This is a subset of the huge ImageNet database, and which has like 1000 categories. So, and another important point is that ImageNet consists of variable resolution images. So like it may contain 23 cross 23, 28 cross 23, 256 cross 256, 64 cross 64, this type of different sizes, but they have downsampled all of them to a fixed resolution, that is 256 cross 256. This is very important because if you are familiar with deep learning or machine learning in general, you know when we try to model a CNN model, simple CNN model with 2 or 3 hidden layers and a dense layer, we have to specify a specific size of the input. So this is a very important line. Now we are coming to the cream part, that is architecture. So like before, the architecture is actually very complex. If you look at it first it looks very complicated. Like if you can see the image, this looks like a lot of information is put within it. So what I will do, I will try to break it down slowly, but first I will explain what are the salient features, like we will read it together through the paper. So the first thing that they have used is ReLU non-linearity. So what is ReLU? If you are unfamiliar, ReLU is the short form of rectified linear units. They are basically an activation function. Like we can use several different activation functions. It's not actually, the main function of ReLU is to add a non-linearity, that's it. So you may ask why non-linearity is important. So non-linearity is important for a number of reasons. I will give a simple example. Suppose we have black and white pixels in an image. Like the black pixels are on the left side and the right pixels are on the right side. The white pixels are on the right side. So if there is no non-linearity, the black and white pixels will create a demarcation line, which is not desirable in an image. If we try to extract a feature map from an original image, we don't want that. We want both the colors to intermix together. So this is a function of non-linearity, and in this paper they have used ReLU. So what does ReLU function do? So ReLU function basically, that every value that is positive, it converts them, it keeps them as it is, and every value which is 0 or negative, it just transforms it into 0. So if the value is greater than 0, it is as it is, and if it is less than 0, it just converts them into 0. So this is the function of ReLU. There are several types of non-linearity that can be used, such as tan H, leaky ReLU, etc., but they have used ReLU. Like if you come across a modern paper which is more recent, you will see leaky ReLU is much more popular. It is very similar to ReLU, but the exception is that if the values are non-negative, it just doesn't transform it into 0. It gives a very small amount, for example 0.5. It just gives a very small amount in the transformation process. So this is training on multiple GPUs. Like they have trained with, I guess, multiple GPUs, 3 GB of memory, and they have used parallelization. Parallelization is distributive computing, which is very handy, and that's the practical usage. When you work on big data, you need this. So now there is another important feature that they've used is local response normalization. So this is a very new concept, and this concept, I guess, in no other paper this concept has been used. So we are basically familiar with batch normalization and other stuff, but this local response normalization is something different. It is actually taken from neurology. So let's see what's the function that they have used and what's the mathematical insights behind it. So the ReLUs have the desirable property that they do not require input normalization to prevent them from saturating. If at least some training examples produced a positive input to ReLU, learning will happen in that neuron. So as I said, if the value is positive, like greater than 0, then the neuron will fire, and if it is less than 0, it will stop. So denoting AXY I as the activity of a neuron computed by applying kernel I at the position XY, then applying ReLU non-linearity, the response normalization activity is given by this expression. So response normalization activity is basically taken from neurology, like how the brain, the neurons actually fire and how they actually work. So you can see that there are several hyperparameters that is being used, such as K, eta, alpha, beta, kappa, eta, alpha, beta, as you can see. These are hyperparameters whose values are determined using a validation set. So they have used this. So hyperparameters are basically the values that we can actually change and experiment with. These values have worked from them for a particular data set. For another data set, for your case, this may be different. So it's up to the user who can use it. So this section again proves that the artificial neural network actually draws insights from how the actual neural network work in human beings and animals. This is the proof. There is not very much information about it, but I think in the internet you can read about it, like what is the intuition behind it. They are clearly used to bolster the Deleuze functioning, but what is actually in their mind behind formulating such an expression, there is no such mention in it, but we can always find it out. So another important aspect that they have used is overlapping pooling. So pooling, if you are unfamiliar with, let me explain it. Pooling, what it does, suppose we have a image, so pixels are there. So what we do, we try to extract the maximum information from an image and try to compress its size. So we don't need the actual image, the entire image we don't need. We just want to extract the meat of the things, like the main information that the image is trying to portray. So that they have used pooling here. Like now, pooling can be of different types, such as max pooling. So max pooling, average pooling, but in this case they have used overlapping pooling. Overlapping pooling is basically you have two pooling layers back to back. Suppose there is an image pixel, then we apply pooling layer 1, and on that pooling layer 1 we apply another pooling layer. So this is basically overlapping pooling. These pooling functions we can see when we go to the architecture and discuss it. So now they have given the overview of the overall architecture. Now this is the crux of the entire paper. So this is all the steps and all the layers that they have incorporated in the AlexNet model. I know it looks very daunting when you see it at the first sight. So you may think what the hell is actually going on here. There are huge number of boxes and whatnot, 3D modeling. So I will try to go layer by layer and try to explain you. So now this is the image. This is suppose we have an image of say 224 plus 224 plus 3. Now the second thing we do is the first convolutional layer. So it is the first convolutional layer. In this first convolution layer, we take a filter size of 11 cross 11 and stride of 4. So 11 cross 11 and stride of 4. This means that in the image, a 11 cross 11 area will be selected and the information will be collected, and convolutional operation will be applied on that part. Now the stride equal to 4 means the stride will move 4 places, and again an area of 11 cross 11 will be selected and the information will be collected from there. This is the convolutional operation. After this, the dimension that we get is 55 plus 55 plus 96. Now you may ask how did I get it? So there is a very simple formula behind it, that is n minus f plus 2p divided by stride. So n basically means the size, the original dimension of the image. So here it is 224 and plus 2p. P basically stands for padding and f is the filter size. So here filter size is 11. So if you do the computer calculating part, so you will get 55. So this is the 55. As you can see, this is 55. So the dimension that we get is 55 cross 55 cross 96. So the next layer is max pooling layer. So in max pooling layer, again we apply a filter and do the computation. After the max pooling, we do convolutional 2, means the second convolutional operation. Here also the filter size is 5 cross 5 and padding is 2, and padding and stride is taken as 1. Like this we perform all the operations. Then the next operation is again a max pooling layer. After that we again incorporate a convolutional layer, then again a convolution layer. That is, till now we have 4 convolution layers. After that convolution layer we again get 5th convolution layer, and after this we get a 13 cross 13 13 cross 13 dimensional image. So I know you can get confused here, but the formula that I have explained before, the n minus a plus 2p, the formula divided by stride, this formula you can use and calculate it. It will be pretty easy. So after the max pooling, there will be a dense, the fully connected layer. So this is the dense layer. So we got 3 dense layers here, and finally we get the 1000 classifications. So I have discussed that they have taken a subpart or subdivision of the entire huge ImageNet dataset, which has 1000 classes. So the final classification result will also be 1000. So in the 1000 values, that will be probability of the image, like in which class it belongs, the image belongs. So you can always read this. So they have given each and every layer along with the number of kernels used and the size and the dimensions. Now coming to the data part. So how do you think the data has been prepared? So the first thing is we have to reduce overfitting. So you may ask, what is overfitting? Let me explain in simple terms. Overfitting is that condition in which there are limited number of data sets, and the image basically learns all the data set. Means it memorizes all the features of the data set and its features and everything. So if you like test the model on a entire new image or say data point, it will completely falter. So this is not desirable. So there are many ways we can tackle overfitting. So a very common step is data augmentation. Augmentation in simple English terms means to increase something in number. Here, if we have images, we apply data augmentation techniques on it, so that with the given number of data we can increase its size. I mean, we can suppose we have 100 images. So for every 100 image, what we can do, we can use some simple operations like flipping the image, resizing it, then zooming it, and basically skewing the original image to produce new images from that. This is called data augmentation. Data augmentation has been a very popular and one of the most effective techniques to reduce overfitting, and there is no surprise that they have also incorporated in this paper. And dropout. So what is dropout? Dropout basically means that when we have a huge network like this AlexNet, there will be a huge number, a lot of neurons in the entire architecture. So some neurons, like in animal nervous system, a neuron may fire and another neuron may not fire, depending on the situation. So dropout basically means we just get rid of the neurons that are not firing at that stage. Suppose in a convolution layer there are 5 neurons. Out of this, neuron 1, 3 and 5 are active and 2 and 4 are non-active. So what we will do, we will basically drop them out. We will get rid of them so that the computational power reduces. And there is a very mathematical reasoning. If you deep dive into the mathematical aspects of deep learning, you will find that as the complexity increases, especially in RNN and LSTM systems, as the complexity increases, there is a high probability that the function, the accuracy keeps on decreasing. Similarly, here, as the number of neurons increases, there is a great chance that the model will falter at various stages. in giving the right answers, in giving the right predictions. So they have used dropout equal to 0.5, that is 50% of the neurons will be dropped off, means they will not fire anymore, and they have been cancelled out. So this step is basically used when we deal with a very complex architecture with lots and lots of layers in between them. So these are just the statistical implications of the dataset that they have used. So this is the learning rate. So you may know how the learning rate was, the stochastic gradient descent, the weight decay, how the momentum works. This is just the training part, and how you reach to the, when you want to reduce the loss function. So how we basically reach the lower portion, the global minima. So this is just the equation of that. So we have a learning rate, we have momentum, and we have a batch size of 128. So if you want to learn this, so you have to start from the very basics of deep learning, like what is a batch size. Batch size basically means the number of data that will be trained in a cycle. What is momentum? Momentum is used along with the optimizers, so that our learning does not get stopped in a local minima, because we want to reach a global minima so that the loss is minimized to its true potentials. We don't want the learning curve to get stuck in a local minima, so we use momentum here. Similarly, weight decay has a function in it. So this is the learning equation, and these are the results. You can check the paper. This is just the data analysis and the results. See, this is the image of a mite, and they have given the probability is highest for mite. Also there is black widow. Black widow, I believe, is a spider, cockroach, tick, starfish. So these are actually pretty close. If you think closely, the predictions of the model are actually pretty close. See, this is an image of leopard. So the highest being leopard, then jaguar, cheetah, snow leopard, Egyptian cat. So as this is a leopard image, so the model truly and rightfully classifies it as a leopard. So this is a mushroom, the mushroom and agaric. Agaric, I am not sure what this is, but they are pretty close to it. I think it is actually, so this is gill fungus and dead man's fingers. These are pretty low in probability. This is Madagascar cat. So you can see how the probabilities the model have returned after a classification task. So the model actually has returned some values, some other values for all the 1000 classes, and they have like aggregated the top 4 or 5 contenders, and they have presented the results. So this was the paper. So I hope you like the explanation, and in the next video I will try to code it live and explain each and every line of the code and the architecture that I have discussed. When I will code it, you will get, this is the architecture. When I will code it, you will get a better hang of what's happening inside, and the other deep learning and basic concepts like max pooling and global pooling, average pooling, what is stride. You will get to know that when I code it. So thank you. Good night.